Grand fam, it's your boy Killer Cam coming at you live from the Buckeye State, ready to serve you with another fresh take of the local expert for MIP 611.
Just kidding. God, could you imagine? Anyways, hello, and if the intro didn't scare you off, welcome back to the channel. For those of you who may have forgotten, my name is Cam Change, and today I'm going to be giving you an overview on three-dimensional cell culturing for this installment of the Local Expert series. I'm happy to report that this is my final episode for this semester, so if y'all rock with me for just a little bit, I promise to tone down the shenanigans and make this thing as painless as possible. 3D cell cultures function similarly to 2D cultures in the sense that they allow for the proliferation of isolated cells in an artificial setting. They are free to grow independent of any changes that may occur in their natural location, or they can be made to endure altered conditions for the purpose of study. The problem with 2D cell cultures, however, is that they are not representative of the cell's true environment. The monolayer or flat surface model causes changes in cell activity that are inconsistent with how the cell would function under natural conditions. This becomes an issue in fields such as oncology and human tissue repair, where accurate predictability is essential for success. On top of that, 2D modeling is at a higher risk for things like cell death and nutrient depletion resulting from waste secreted by neighboring cells. 3D cell cultures can provide real-life context by allowing the cells to act the way they normally would in endemic environments. 3D cells have the opportunity to maintain their true morphology and differentiation, which allows for better retention of important features like polarity, reproduction speed, genetic identity, and gene expression. 3D modeling can also facilitate realistic intercellular interactions as well as lifelike extracellular matrix responses, allowing for more predictability and accurate results in experimental designs. It is estimated that 3D culturing hit the scene sometime in the 1970s via floating collagen cells that were developed from conventional cultures. Seeing the potential for this type of technology, experts in scientific fields ranging from inorganic chemistry to bioinformatics poured their resources into its development. Their efforts gave rise to three-dimensional cultures as we recognize them today, and are conducted via scaffold or scaffold-free techniques. As it might suggest, scaffold techniques occur when the cells are cultivated in the presence of supporting structures. This usually happens one of two ways. Hydrogels, where cells are either embedded or coated onto a water-saturated polymer network, or polymeric supports, where they are cultivated in the presence of fibers or sponge-like structures. With the scaffold-free method, cells are allowed to form non-adherent aggregates known as spheroids. This allows the cells to secrete their own extracellular matrix just as they would in vitro, for example. The choice of technique to use in 3D culturing is largely dependent on the cell line and origin, as well as the study's end objective. As with any other budding technology, there are still some kinks in 3D culturing that have yet to be worked out. The first of which being the financial investment needed to conduct these procedures. When compared to conventional 2D models, the materials needed to carry out and maintain 3D cultures are significantly more expensive. These materials are also harder to come by because there are fewer commercial vendors available that offer these products. On top of that, 3D cultures can take longer to proliferate than 2D cells. Additional lag times can pose a problem in bacterial drug trials, for example, due to how quickly antibiotic resistance is transferred between microbes. Another thing to consider is that depending on the size of the culture, it can be difficult to disseminate things like oxygen or essential nutrients to the correct locations. Lastly, because of the complexity of the culture, there is a smaller reducibility rate for 3D mockups, and the results are oftentimes more difficult to interpret. When listed out, the challenges can make it seem like 3D culturing isn't a worthwhile venture. But if we keep everything in context, it's not difficult to see that the benefits far outweigh the costs. Remember, 3D modeling helps to preserve the morphology and functionality of the specimen. This means that we can assume that cells being studied will react similarly to the way they would if they were still in their natural habitat. Imagine what that could mean for the success rate of experimental cancer treatments, for example. Plus, it comes with an added speed and ethical incentive as well. The more we can correlate the results from 3D culturing to those seen in real people, the less we'll need to rely on animal testing. With time, it could even be possible that 3D cultures could reduce the animal testing step and shorten the experimental treatment pipeline altogether. Regardless, the one thing that we have to remember most is that science is never stagnant. Researchers are constantly working to overcome issues and barriers in all technologies, including this one. With all this in mind, one has to conclude that the ends justify the means when it comes to 3D culturing. To learn more about 3D cell culturing or other related topics, ask Professor Borley or Ariel because I ain't a doctor. But if you insist on doing your own research, feel free to check out some of the links that I provided. Well, that's all the time for me, guys. I would like to thank you all for sitting with me during this installment of the Local Expert Series. Again, my name is Cam Change, and I'm Audi 5000. Later.